Okay, last class we saw the evaluation of deformation by integral methods. In the sense, W of y, we put it as a y eta, z eta, d eta. This is the integral approach, and this is the solution of basically the deformation for a given loading condition. But you can write the differential equation of deformation, which we wrote it as beam bending equation, very simplified. We wrote EI okay. This is a differential equation form. Now EI is a constant, you can take it out and you can solve this fourth order differential equation, apply the boundary condition, and then you can get the W. Now similarly, this is a one dimensional problem, in the sense we said W is only a function of y. Suppose in the case of wing, if you draw the wing as such, approximately this will be like a, this is your x axis, y axis, this is my z axis. So the wing is in a plane, and any small element, you can have the lift force or the pressure. This is a two dimensional problem. In this case you can write similarly, like you say any x y, W at any x y, it will be an area integral. You can put a double integral, and your influence coefficient will be x comma y. You can have eta, zeta, z, eta, zeta, d eta, d zeta. Okay. So this is like the deformation at x and y coordinate due to a loading at eta zeta, and the elemental area is d eta d zeta. So you can have this as, this is the d eta d zeta, this is the z at eta zeta. So deformation at any point you can take x comma y. Okay. Now this is all in the integral approach you have to get. There is another approach of getting the deformation, which is, I will erase this part, which is the energy formulation. So I will write the, so you can say energy formulation. See, this is another approach to solving the structural problems. But then you may ask, why do we have to use it? You can always have force balance, like what in the earlier case, we balance the vertical force, moment, and then you write your equation, moment equation. That is based on Newton's law. Okay. Energy approach, you are dealing with the scalar quantities, because energy is a scalar, whereas in the other approach you deal with vector quantity, which means this is coordinate independent. That is number one. Number two, the advantages of using energy formulation is that it will give you the differential equation, and it will also give you the boundary conditions properly. Whereas in the force formulation, like Newton's law, if you put a tip mass like a missile or anything on the tip of the wing. What is the boundary condition you have to impose there? Okay, these things you have to be very clear. Whereas the energy formulation, when you follow that, not only you will get the field equation, you will get the boundary conditions also as a part of it. But please remember that this is not going to give you the solution, it will give you the equation. Another approach is in the energy formulation when you want to get approximate solution. Okay. The conditions which are imposed on the choice of functions is less stringent. I would put it that way, less stringent. Okay. But whatever I have said in words, you will get to know as we proceed further, because with examples we will solve. Then you will understand, oh, this is the reason why energy formulation is quite attractive. Now the question is, energy formulation you can do for static problem, you can do for dynamic problem, both. You can have static, you can have dynamic situations. Okay. But we will go through the approach. First we will do the static and then we will do the dynamic later. And if you look at the different books, some books will deal with the same static dynamic problems for rigid bodies. Okay. In another approach, you can say deformable bodies. You can do the same thing for deformable bodies also. So you can have rigid body and deformable structure. Okay. Please understand, you can have this formulation for this or this, but if you, the approach that is adopted to get the final equation for rigid body is one form. When you go to deformable body, it's in a different form. Okay. But both will lead you to the same final form of the equation, which is like you may call it Lagrange's equation or Hamilton's principle. We will come to those two later because these are very important. Lagrange's equation, okay, or Hamilton's principle. Okay. We can apply this for dynamic situations. Okay, dynamic situation. But they are derived from, all these are obtained from essentially principle of virtual work. Okay. The energy formulation, if you see, it starts with the principle of virtual work. Okay. What do you mean by virtual work? We will do with the example case, very simplistic situations, so that you get an idea of what do we mean by virtual work and how that is applied to get our energy formulation. Suppose we will take a very simple case, which is like a, you all know, a string with a mass m. This is a string length L. It is in static equilibrium. Okay, and under the action of gravity. That means what is that? If you draw the free body diagram of that mass, you will have mg and you have some tension T. It is in equilibrium. So T minus mg you say is 0. This is what you write. Okay. Now in the virtual work, what you do is, in the equilibrium position, if you give a virtual displacement, please understand, it is not an actual displacement, it is a virtual displacement. Now, what is the virtual displacement you can give? Please understand, the virtual displacement must be consistent with the constraint in the system. That is important. This must be consistent with the constraints. Constraints in the system. Okay. Now, what is consistent? Here we said that length is constant. That means it cannot extend. We cannot give a virtual displacement in the vertical direction. You can only give a virtual displacement in this direction. You can give a virtual displacement in that direction. Okay. That is allowed. But then you know that if I calculate the work done means the virtual work done, because the forces are actual forces. Okay. And I am doing a virtual work which I call it delta, because this is the symbol I use for virtual. Delta W. Okay. Now what happens for this system? It is T minus mg is the force that is acting on the system. But I cannot give a virtual displacement in this direction because length is fixed. The static situation. That means this is out. I can give a virtual, but this displacement, virtual displacement, is 90 degree to the force. Therefore, the work done in this case, it is nothing but T minus mg into delta. Maybe I call this as delta y. But this is at 90 degree. Okay. Therefore, the dot product goes to 0. Very simple. If this goes to 0, then T is equal to mg. Then you may say, what is that? It's a very obvious situation. Okay. Now we take a slightly different. So the principle of virtual work is basically what? For static equilibrium of the rigid body, you say delta W static equilibrium. Delta W is all the forces that act on the system. Now I am going to slightly modify the example and then change this itself into a different format. Let us say this is only a simple example. Now we take another example which you are all familiar with, which is like I have a spring, a mass, and this spring is K, and you have applied a force F, and it has deformed through a distance x. Okay, it has already deformed through a distance x. So you know from static equilibrium, F is the external force. And let me put it this way, I think I will go here. On the mass, you have basically a kx which is acting in this direction, there is a force F is acting, of course there is a normal which is the ground reaction that may be balancing with the gravity, okay, N is empty. Now in this problem, what is my virtual work principle? Okay, how it will look like. Now I know the forces acting on that body and it is constrained to move only along the x-axis, only in the horizontal direction. This can move only, it cannot go vertically. Therefore, the N and G, they can't do any work, okay, but it can move in a horizontal direction. If it moves horizontally with the virtual displacement delta x, now what will you do? You will have minus kx delta x, that is this force doing a displacement through a virtual displacement which is delta x. This also does F delta x. Okay. Now, as per our thing, this is 0. Okay. But now what I have done is, I am writing this force into this as I am going to write delta W. This is the virtual work done by the external force. I am going to call the spring force as an internal force. Okay. Like in that. Now the spring force, you know that energy of a spring is K x square, right? If I have a variation in the energy, which I will write it as what? Delta U over, that is variation in the sense, the variation in strain energy due to a virtual displacement. This will be, you will do the same thing. It will become delta x. Okay. And that is this term. So I can write this is minus delta U okay. Now you see what is my virtual work principle is simply I am saying delta of W external equals delta U. This is one form of writing. One form of writing. Another form is you can write it as delta minus U. This is another form of writing. This is like delta, you take it as something like a first derivative, even though it is not first exactly first derivative. It is like, please understand, it is a virtual displacement. This is the variation due to a virtual displacement. And first variation is 0. This is a function. First variation 0 means first derivative. When you take it is equal to 0, it's a maxima or minima, right? So you call it, generally people say, this is the principle of minimum potential energy. And you define this as potential energy of the system. So you say principle of virtual work. From here you get the principle of minimum potential PMPE, principle of minimum potential energy. Okay. This is the principle of virtual work. That is delta W external equals delta U for static problem. Now I just want to, I will not derive, but I am going to ask you to think in the sense, suppose I am having, see, I have taken a simple problem like this, simple example, very simple example. Suppose for, let us take another simple example, which is like a beam. It is supported at some two ends. I am applying the some F here, external force. Now how do I write the virtual work? Okay, because you say the reaction forces are here and they are constrained, they cannot move. You understand? So that means the virtual work done by this 0, but the virtual work done by this is there, it is not 0, and that is the value which is the delta W external, okay, which goes and gets stored in the variation in the strain energy of the deformable structure. Okay, now how it deforms, that is what we have to calculate. So essentially the principle goes like this. When you apply a load, the structure deforms to some shape, or you can call it some configuration. Okay, that configuration you may say, I will just draw by single line. It may be like this. Okay, but it is one. When I apply that F, it deforms always in the same configuration. Why it chooses that particular configuration? Why can't it choose slightly different? Okay, slightly different. Any other varied configuration. You follow? Why it chooses that particular deformation, you may call it pattern or configuration or anything, among all possible configuration. Because you can have like this also, and you can define like this also, some another line. There are several ways, but it chooses only one. So essentially what you are saying is, it chooses that particular configuration for which variation is 0. First variation is 0. That is like a minimization problem. Actually, maxima minima. That's why people don't call it, even though principle of minimum potential energy is mentioned. Actually, in dynamical system, they write it as extremum. Can be minimum or maximum. People don't go and derive the second derivative. Okay, but it is mentioned as minimum potential, principle of minimum potential energy. Now you have got an idea how virtual work principle is used for structural analysis. Okay. Now let us say that is, this is the, understand, static. The same principle is extended to dynamics. Okay, but that we will do later. First we will take the static part and I will do one example problem how this principle is used in getting the deformation of a wing, you can say an approximate wing. Now you write the deformable structure. What happens? You are applying a load. Let us say you apply load at several points on the boundary you will apply. Okay. Now fx, which is a function of x comma y comma z, Fy some other, and Fz. These are the forces acting on boundary. Okay, acting on a boundary of the structure, and they are going to do the virtual work. So what you do is every point in the structure undergoes, because of the application of load, they undergo a deformation. The actual deformation, you may call it U, V, W. This is the actual deformation because of the application of the load. And this is, you may say, a function of, because x comma y comma z, because this is the point x y z. This is an identification. Okay, and how this point has moved after the application of the load. Now that the deformation pattern, or you may call it deformation configuration, you are going to represent it in terms of several functions. Okay, known functions. Those functions satisfy the boundary condition. Okay, so you may have the coefficient of those functions are basically the unknown. So you represent them by Q, and these are my unknowns, you may say. Okay, later I will show how this is applied. Similarly, you will have V, which is a function of, which is actually again the identification point, again it will be, and W, that is also Q12. Okay, you may call it, these are the unknown, these are the generalized coordinates, you may call it by any name, that is unknowns are generalized coordinates, you may call it. Okay. This is the actual displacement, I am representing like this. Now what is the virtual work done? By the virtual work will be only by the surface forces. It cannot be by internal, because external W external is external. If you have body force will do the work. But here we neglect the body force for the present. Okay, we will take the external load. This is on the boundary. Here is this point. And we will write our delta W external. This is a surface integral Fx delta U Fz delta W into d surface. Okay, this is what we have. Now we need to see how delta U, delta V, delta W, we can write it in terms of this what we assumed. Okay, you can write it as, maybe I will erase here. Your delta U, the variation in U is due to variation in every one of these generalized coordinates. So you will write it as delta U by delta Q1 del Q1 plus so on U by and which can be written as summation delta Q I running from 1 to n. Okay. Similarly, you can write for V, you can write for W and take this and substitute here, and what you will get? You will get delta W external is integral S is there. You are going to put a summation I running from 1 to n Fx delta U over delta Qi, okay, plus Fy delta V over delta Qi, Fz delta W over delta Qi, and I put the bracket here, del Qi, and you have a ds surface. Okay. Now what you can do is, these are virtual displacements. Okay. Each virtual displacement is, each is an independent coordinate. So each you can give independently the virtual displacement. So you can take the integral inside and write it as summation I running from 1 to n integral, you can put it Fx delta U by delta Qi plus Fy delta V by delta Qi plus Fz delta W by delta Qi ds into delta Qi. Okay. This is only on the surface. Now this entire expression you can write it as delta W external is, you will write it in this fashion, Qi into small I running from 1 to n. This is my generalized force, this is my variation in the generalized displacement. How do I get the generalized force? Qi, Qi is nothing but this integral, this integral. Okay. Now let me erase this portion. You have to get now expression for U. So let me erase this. Because here also it is very simple, because U, V, W are actual displacements. So virtual displacements are functions of these. So your strain energy is going to be a function of Q1, Q2, Q3, Qn. So you can simply write U, which is a function of U, Q1 to Qn, and del U will be, you will have summation delta U, sorry, capital U, delta U by delta Qi del Qi, I running from 1 to n. Okay. Now what you are doing is, you are equating these two. When you equate these two, summation I running from 1 to n, I running from 1 to n is gone. What you will have is Qi becomes delta U by delta I running from 1 to n. Okay. This is my equation basically. You will find that this will become an algebraic equation for a static problem, beam bending problem. We will show that. And this is called Castigliano's first theorem. Okay, it is called Castigliano's first okay. Now we have put n only up to n. Suppose if this number goes to infinity, beyond, actually n keeps on increasing, it can be shown that you will get the exact result for the deformation. It will approach the exactness. And this particular, using this technique with finite n, that's called the Rayleigh-Ritz approach. Okay, Rayleigh-Ritz approach. But please understand, this is what we will use. See, this we obtained from the virtual work. Please remember this equation, this virtual work principle, it is not balancing the energy. Please understand, it is not an energy balance. You have to know. It is because you can have a non-conservative force, anything you can have. This is basically about equilibrium point, okay, or equilibrium deformed configuration. Any variation about that equilibrium, that is what zero. That is why this is a minimum or minimization approach. Actually, when you transfer to dynamic situation, that is actually also called principle of least action. Okay, it comes from calculus of variation, or you can say variational calculus. Okay, so the dynamical system is exactly similar to that. That's why variational calculus, Hamilton's principle, is exactly like that. First, that's for dynamic systems. So please understand, this is what we will use for our static problems. Energy approach, you want to get the deformation of a wing, how do I solve? Okay. So now we take one example problem, very simple example problem, and you will know how we are obtaining the solution to the wing deformation. Please understand, earlier we had the integral formulation. Okay. Now we are going to have the energy formulation. What we will do is, we will apply it to a continuous system. That is our, in this case, this is a Rayleigh-Ritz approach. Okay. Principle of virtual work applied to continuous system. Our problem is very simple. What we have used earlier, we are going to represent our wing like a cantilever beam of length L. Okay, and the properties are, you may say, EI is the property of the bending stiffness of the beam. This is acted on by, again, some external loading, which we call it as theta y. Okay. Now we want to know how do we get the deformation of the beam, and let us write the deformation. This is W, which is a function of y. Okay. Now the first thing what we do is, before we go and then start writing everything, What we want to obtain? We want to obtain the deformation. So I am going to assume that my Wy is approximate. I am approximating it, please understand, with the gamma I, which is a function of y multiplied by qi. Now you will be able to understand. I wrote UVW. In this case, I am not interested in UV and other thing. Only vertical deformation, that is why W I am interested in. Okay. If you are interested in every other deformation, then you have to write correspondingly. We are interested only in bending deformation. That's why W as a function of a generalized coordinate. This is my generalized coordinate. Okay. Now what are gamma i's? Gamma i's are my assumed deformation shape. Okay. So you may call it, these are my assumed deformation. You may call it deformation function. Okay. But the important thing is, this is your choice. Okay. What is the assumed deformation functions? What is the condition? Is there any condition? Because you have to know that any virtual displacement you give, they must be consistent with the constraints. Okay. My constraint here is, it is fixed here. That means when I have fixed boundary condition, I cannot allow displacement 0 and slope. I cannot allow displacement is 0 and slope is 0. Okay. That means I must choose those functions where gamma I is 0. Okay. Then d gamma I over dy at 0 is also 0. Huh? Second derivative y. Changing where? Who said that it is not changing? Why? Second derivative is what? Moment. Is the moment 0 at the root? So that's why these are geometric boundary conditions. Okay, I'll write it as geometric boundary conditions. Okay. So please understand, my assumed deformation function must satisfy geometric boundary conditions. So I will write it satisfy geometric boundary condition. That is the condition we should have. Suppose if you say, no, I don't do that, then your error will be more in your result. You will get a result. Please understand, in this you will always get some number. Okay, but how good is the number is the question. Because you are seeking approximate solution. That's why the choice of the functions is very important. Okay, because in vibration they are also called admissible functions. Okay, admissible. What are the functions which you will accept or admit? So you may call it admissible functions. Gamma I may put it admissible functions. Okay. Please understand, both mean the same thing. Admissible functions are assumed deformation functions satisfy geometric boundary condition. Actually, admissible function is one which satisfies the boundary. So the terminology is admissible function. All right. Now what you do is you have chosen a deformation, assume a deformation shape. So I erase this part, write down the external work, virtual work and the strain energy part, okay, and then apply this equation. You will get your solution, or you will get the complete set of algebraic equations. So let us write what is the virtual displacement? Delta Wy is nothing but summation I running from 1 to n gamma I delta Qi. This is the virtual displacement. Now delta W external is 0 to L Fz, sorry, not Fz, that is Zy, okay, delta Wy. So I can write it delta Wy dy, you can put it. Now you substitute delta Wy, this expression here, and then write it as 0 to L, okay. I am putting a summation outside I running from 1 to n, z of y gamma I y dy into delta Qi. Okay. So please understand, I have substituted here, I have taken out the summation outside and put the integral. Now this is my generalized force. Got it? That is the Qi. So you see, it's very interesting. What is generalized force is nothing but the actual force multiplied by your assumed shape function or admissible function. Every function you take, you multiply and you integrate, because you have to integrate over the whole thing. Okay, so this is my generalized force. So your actually actual force multiplied by the assumed shape function. Now similarly you have to write the strain energy. Now we got external delta W. So please note that this W is different from this W. Okay, don't have a confusion over the W's. This is deformation, this is the work. Okay. Now what is the strain energy in a beam? Because the general expression for strain energy, you always write integral half sigma epsilon, because in a deformable structure you always write like this. This is the volume integral. Okay. Sigma epsilon d volume. This is your general expression for strain energy. Now you are solving a bending problem. You have to substitute for epsilon. What is the theory you have used? We are using, if you say Euler-Bernoulli beam theory, okay, if the beam cross section is some shape, then you will say, okay, how do I represent my epsilon? And then that epsilon you will substitute here, and then you know stress is related to strain, okay, because this has all the components. Sigma epsilon I wrote, basically it has xx, epsilon xx, ij, everything. That whole summation is there. All right. So if you want, you can put actually ij, something like that. You can have everything. But in this case, you will have only normal string epsilon xx. Okay, and you substitute, you get the sigma, which is stress strain relationship, and where your material property will come in. After that, you integrate, and when you integrate, you will finally get, I hope you know this part, otherwise I will write it, half, you will write 0 to L, because cross sectional integral will be taken EI d square W by dy square whole square dy. This is what you will have. Please understand, for the beam bending problem with the Euler-Bernoulli assumption, all those things are there. That is why I am not, this you are familiar with, right? So that is why I am not deriving all this stuff. So this is the strain energy of the beam under bending deformation. Now what you do, you go and substitute this expression here. Okay. Now you see an interesting part comes in. You have to take the variation. Okay. Now when I substitute this, because we assume that W of y is summation gamma I y ui, gamma I ui. I need to take second derivative of this function. Please understand, because though I mentioned that it must satisfy the geometric boundary condition, another condition which comes is it should be differentiable in this case 2 times at least. Okay. So that is also equally important. Okay. But you will see, now I am going to substitute that function here, and then this is a square. So this will be actually I, so you can put it ij, 2 indices, and sum it up over both I and j. You will write this as half summation I running from 1 to n, summation j running from 1 to n, integral 0 to L EI d square gamma I over dy square, d square gamma j over dy square dy into qi qj. Okay. Now please understand, this is a 2 times differentiable. All right. Later I will tell you what is the essence of this. Now you have to take the variation. When you take the variation, this will become delta u becomes summation I running from 1 to n, summation j running from 1 to n, integral, because qi qj, actually it is a square term, there will be 2 terms will come. So what will happen is the 2 will cancel out with these 2 if you really expand everything. Okay, that is why the 2 I have not put in here. You will have 0 to L EI d square gamma j by dy square dy. I will put this in bracket, and then I will put a q j, then I will add another stuff. I will put it delta qi. Okay. So this integral you can evaluate. That is not a problem because you know ei. Now please understand, in this formulation I don't need to assume ei to be constant or anything like that. Ei can be varying function. Absolutely no problem. So ei, only thing is you need to integrate. Either you can use numerical integration. If you have a closed form, you can get the closed form integration. Now you have to equate delta w external and this one. And then since delta qi's are arbitrary, I will write that part, then you will be able to see this is the final. So you are going to use this delta u minus is 0. Now I have my expression for delta u, I got my expression for delta w external, I have to write. So this I am writing summation I running from 1 to n, I am putting opening a big bracket, summation j running from 1 to n, integral 0 to L, ei d square gamma I over dy square, d square gamma j over dy square dy into q j minus integral 0 to L z y gamma I dy, okay, delta q I equals 0. Okay. Now you say my delta qi's, because qi's are the generalized coordinate and I can vary each one of them independently. Therefore, these are independent. That means the term that is getting multiplied to that delta qi must be equal to 0, and that gives you your equation, which is summation j running from 1 to n, integral 0 to L ei d square gamma I by dy square, d square gamma j by dy square dy q j minus integral 0 to L zy gamma I dy equals 0, and this is I running from 1 to n, because you will have n equations. Okay. Okay. And this is a algebraic equation now, because you know ei can be a function of the wing full, it can vary, because like a wing I is changing. Okay, if it is assuming uniform material is same, and d gamma I by dy square, d gamma j, that is the second derivative, you multiply, you integrate, but only thing is ij you have to keep repeating it, but it is a symmetric. When I becomes j, j becomes I, it is the same thing. Okay. Now this looks like some kind of a stiffness matrix. See, because I can put it in a matrix form, right, because k, every element is this, Q is this. This is my capital Q, which is the generalized force. Now I can solve for Q. But please understand, I am only solving for the generalized coordinate. After that, I have to go and substitute to get the deformation is summation gamma I y Q. You follow? Now this is just an algebraic equation, and K is symmetric. Okay. Now you can obtain the deformation of a beam. Now this is a very powerful technique for obtaining an approximate method of Rayleigh-Ritz approach. You can also do it for dynamic situation. But just to deviate a little bit, you know bending equation last class we derived, which was d square by dy square EI okay. We wrote like this, and then this is a fourth order differential equation. We need 4 boundary conditions. Please understand. And the function W, whatever you assume, has to be differentiable how many times? No. Here it is differentiable by 4 times. Here twice. Okay. So you see, that is the attractiveness of this, because exact solution if you want, that is the only approximate solution. Please note, in the limit n tending to very large, okay, it approaches the exact solution. But here getting an exact solution for is not easy. Okay, it's a very difficult task. Whereas you can go ahead and do approximate solution, and normally what you do is you take more number of gamma I and you show convergence, how your deformation has converged with the increase in the number of assumed shape function. Okay. So the exact solution is the one which should satisfy 4 boundary conditions. 4 means 2 on this side, 2 on that side. These 2 on that side only the force boundary conditions. You will have the shear force, bending moment boundary condition. Here you have displacement boundary condition. Okay, they must be satisfied, and in addition it should satisfy the differential equation. Now you see, that is the exact solution. Whereas here what we have done is, we are not bothered about the force boundary condition at all. We simply used geometric boundary condition. Okay, like displacement and slope 0, and it is also differentiable only lower order. So that is the attractiveness of the energy method. You want to get approximate solutions for a complex, because not all problems you can have exact solution. Please understand. Any general wing structure you cannot get exact solution. You can always, you have to go for approximate solution only. And this method is very, very attractive. And this is what you will be using in this course. Okay, I will give one more assignment which I will send it to you, which will be related to this particular problem. Okay. Okay. This is energy formulation for dynamical systems. Okay. Now, like I said earlier, you can derive this for deformable structure, or you can derive for rigid bodies. Okay. If you look at the classical mechanics books, they will start with rigid bodies, particles. So they will get the Lagrange's equations, Hamilton's principle, everything from here. So what I will do is I will follow that approach, but the final result is applicable even for flexible deformable structure. If you follow deformable structure, it is identical. Okay. Only thing is you have to take the boundary condition and etc. external work done by the various things, apply the boundary condition, equation of equilibrium, everything will be applied, and then you will finally arrive at the same Hamilton's principle. Okay. So what we will do is, I will do for the rigid body thing. The first thing is, in rigid bodies we have constraints. What do we mean by constraint? Okay. If we have one free particle, it can have 3 degrees of freedom. Particle x, y, z. If you have 2, you can have 2 into 3, 6. Suppose if you have n particles, you will have 3 n degrees of freedom. Okay. Each one is independent if they are. Suppose not all of them are independent. They cannot move each one freely. There are constraints in the system. Constraints in that system in the sense, what type of constraints? Constraints will relate to the coordinates of each point, because 3 degree of freedom, when I say x comma y comma z, the particle is moving. That means x is changing with time, y is changing with time, z is changing with time. If I have n particles, again all the particles x will change with time. But if you say like a rigid body, when you talk about, if you take 2 particles, the distance between them is always a constant. That means what you are doing, you are putting a constraint. Not that everything is free to go as they want, but you have constraint between the particles. That means these are constraint equations, they say. Okay. Constraints, or you may say constraints. But what type of constraints? They can be, because I can write it, constraint equation can be x comma y comma z, because time is also there. With time they can evolve. This can be equal to a constant. Okay. Time can be explicit, time need not be explicit, but this is a equality constraint. Involving, please understand, only coordinates, that's all, and time, not their derivatives or anything like that. Okay, it's only these type of constraints are called holonomic. Okay. That is equality constraints. Any constraint which is written in this form is a holonomic constraint. You can have another type of constraint where suppose a particle is inside a box. It should not go out. That means its position is constrained within the box. That means it is a inequality. It can be inside or it can be on the boundary. It cannot be outside. Okay. Now these type of constraints are non-holonomic constraints. That is not equality, but it can be greater than or less than or whatever type. Okay. They are non-holonomic. See, one example which they say is a particle must be position r, which should always be within some bound. Okay. That means you can say that you can, if it is a sphere of radius a, and you want it should be always r can be less than, suppose you can say it can be always outside, okay, greater than 0, it can only come and then that means the particle can never come inside. Okay. Now, yeah, you can have derivative constraints, but normally in coordinate, because all are the position in dynamics is described with generalized coordinates. Generalized coordinates for one particle 3 degree of freedom x, y, z. Okay. So the constraints will be only in terms of this. Okay. But you can have another type of constraint where differentials will come. The differential is one of the examples that is given is a rolling disc on a ground. Okay. And in that, the constraint, it cannot go up, and the distance traveled is actually velocity, because it is rolling without slipping. If you put all those conditions, then v is a omega. Now it is a velocity constraint. Velocity is actually derivative of the displacement. Those type of constraints are also non-holonomic, because they cannot be, they are not considered as holonomic constraints. Treating them is different. You have to treat them separately. Only holonomic constraints of this type can be easily considered, but actually the validity of the whole approach is not restricted because of this. Please understand, it is still, many situations it is applicable. Actually the whole theory started with I think particle atomic level vibrations and things like that. Okay. Even suppose a bead which is sliding on a string and the string is moving. Okay. Now these type of constraints cannot be written in this fashion. A bead which is sliding, but the one of the problem bead sliding is similar to, I'll say this problem I thought I will let you know. I wanted you to derive later. That is, this is also an aeroelastic problem. You have a pipe, okay, and the fluid is going in. You treat the fluid as the fluid mass. Okay, I am approximating this whole thing as this is a something, and in this the mass is moving. But this pipe also can bend. Okay. In this situation, how will you write the equation of motion for the beam or pipe? Like if you take a bridge, the rails are, it's like you have a pillar, this is a railway track. On a railway track, some mass is going. That means what will happen? This bridge will bend, and this is going down. This will actually have, even though this is moving this way, the bridge is bending, you will have a bending load coming in. This problem is a little axial flow. All these problems are very similar. You can derive the equation. I would like you to try. Just assuming that this is a fixed point, starting point. This is a particle. The particle is moving to the right on a string, but the string is having a displacement w, which is a function of x comma t. This is, you can take it as, sorry, this is x, and this particle is having its own velocity. Okay. Now you write what is the acceleration of this mass in vertical direction. Okay. Just that expression. Then you will find this is very similar. This equation directly you can use flow through a pipe. And if the velocity of the flow increases, the pipe will start getting into some vibration. These are all there in nuclear reactors where the cooling thing, because it will start. That is also one of the aeroelastic problems. The flow creating this. Another aeroelastic problem, of course, that is the fluttering of a flag. That also, when the wind blows, it does doing. Okay, that's also an aeroelastic problem. All these are, but modeling each one of them requires different approaches. Okay. Now let us take this as a holonomic constraint, and what we will do is how these constraints are represented when you give a virtual displacement. What? Because when you have constraints, the number of independent degree of freedom will get reduced by how many constraints you have. So you will finally you will have only 3n minus c. This is the number of constraint, not constant. This is number of holonomic constraints. You may say you can take number of holonomic. This is my final degree of freedom, and these are independent. Okay, this is my degrees of freedom of the system.